Welcome. Today I'm going to be flow testing the transfer ports in my 100-mile-an-hour moped challenge cylinder to see if I've got enough time flow area for the power that I actually require. Also, I want to see if those figures match up with the calculated specific time area figures STA that were calculated in EngMod 2T. And also, if you're wondering, we'll have a look back to see where the specific time area figures originated from. And as you know, with two strokes there's always a problem, and that is that the scavenge flow direction also does play a major part into how much power is produced. So if you're interested in how that affects things, then we'll have a look at that a little bit later in the video. Firstly, big welcome to all the new subscribers. I haven't uploaded much, and I think in the last 3 months I've actually gone up 1,000 subscribers, so people are still hitting that subscribe button even though I'm not putting out much content. So for me, I need to get some more content or add to the conversation, and I guess for me it'd be good to get to 10,000 subs by the end of the year. So if you do enjoy what I'm putting up and you do enjoy this video and you're not already subscribed, then yeah, hit that subscribe button. Right, before we go into all the stuff here, a couple of shout outs. Firstly, young racer we know, Rhys Stevenson. Rhys has previously raced British mini bikes. He then went British Talent Cup into the Red Bull Rookies as well for a season. It was really cool. He's now in the National Sport Bike Championship. Fortunately though, he had a massive crash at Knockhill the other weekend, so bike very bad, and yeah, it costs a lot of money. So really it's a shout out if anyone wants to go and support him, check out what he's doing, maybe give him a helping hand. He could do it because it's a family run team that don't have a massive budget, but the guy is rapid, spends his time in the paddocks, you know, giving out information and teaching the younger kids how to go faster as well. So already he's giving it back, so it'd be nice to give him something. Other things, so 2-stroke stuff, so 5 power 2 strokes, YouTube channel. He's been currently putting a KX85 engine into a Kawasaki AR frame, which is good. It should go really fast, and if you want to check that out, you got his channel, 5 power 2 strokes. So first attempt at 3D printing for a while. So far, so good. It's just supposed to be a test print, but if it works okay, I'm going to go for it. So I'm not going to bore you with a time lapse of 3D printing. I'll meet you when it's done. So 3D printing done. Took 4 hours, and that's what we got. Little transition into the cylinder against there. You see a bit better. See if the tube fits in. 3D prints come out quite nicely. Tube fits really nicely. That transition's good. I'm just pulling this support material off now. I don't know if you can see, but I put the O-ring groove in, so it will seal it as well. And obviously this bit that it locates off that bit, so I'm just having a bit of a game pulling that off. I put this tube on with this metal in the middle, just so when it went in the chuck, I span it up and just cleared out the raft material. Bought a nice edge to that, cleaned up the O-ring groove, and I put an O-ring groove in there. I should have 3D printed these in, but I didn't because I was in a rush, but I've just drilled them through. So now you see this will locate on here. Okay. So that's located on there. Then drop these bolts through. So that's on. I might have to do something about this. I might have to get some other M8s, because that's just going to affect the flow going into there. So I'll swap that out. I'll get the fucking fat fingers down there. But it's a nice transition all the way out into the Hoover. Right. So I need to know where that piston is, because the only part I'm going to be able to measure it off is this, because the lid's going to be on it. So what I've done, I've put that piston ring, so it's at 39.1 mil as measured with my verniers. So I now know it's at 8.9 mil from there to there, and I'm at 31.9, which is just where the port is opening. So 8.9, I can set that, turn it off, and then I can then push down, a bit like I was doing last time, keeping it nice and square. So I know that's 8.9mm. It should give me, as accurate as I can measure. These aren't the best things for measuring, but 31.9. So yeah, that allows me to position that piston where I want it. Eventually it's going to come about, protrude 1mm from the edge of here, but that should allow me to set, and I'll do flow tests at every 1mm of opening of the transfers. Just preparing the cylinder, so I'm going to block off the exhaust port using my leak down tester. I've got a couple of wasted nuts. Just turn them down on a lathe. You'll focus. Yeah, just to give a little bit more clearance. You'll see in a minute. And then I'm just going to bolt this on. Right, brief overview of the setup. So, the modelling clay, or plasticine, whatever you want to call it, it's just around the entry, just to smooth the outflow, because obviously if you had a sharp edge, the flow would naturally go over there, ultimately making this area a little bit smaller. So the idea is it allows the flow to attach here and then use the full area of the transfer ducts without affecting it. So piston obviously controls the distance, so I can set a distance here which relates to a distance for the top of the piston as it uncovers the transfer ports. I've already written this down, so I've worked it out. I've already did a test just after Christmas, so Boxing Day. So when I measure 7.9 distance here, that equates to the piston being 32.9mm from the top, which is 1mm open of the transfer ports, because they actually start opening at 31.9. So I'm just going to go through again with all these different positions, measuring it with that, and then I'll collect the data and then I'll put it through the program. So yeah, pretty much as before. Plasticine, pistons in there, that's blocked, that's blocked. Got the Venturi. One of these manometers will do P1, the other one will do the differential pressure, and then I'm going to control it with the vacuum. I've had a run through, so initially I do have to run it on the lowest setting with this fully open, but I can get up to the maximum pressure, and as you can see we're just doing a P1 pressure of 300mm of water, so it's a constant pressure as opposed to the exhaust where it's give it as much as you can. So the first is I need 7.9. That's locked off. Happy with that. Ready for the next test. That's the base run I'm going to do two separate tests.
So here we have the TorqSoft software, pretty much the same as the exhaust. So I'm just going to bang in the figures. So I've put in a P1, all 300, and now I'm just going to load in the delta. So that's that, and I can calculate. So I'll reveal the result once we go back to the SDA.
I'll now move on to a bit of specific time area, or time area, or angle area. Loads of different ways. Gordon Jennings, I think, probably brought it to the light of the public first, maybe, on his way. And I think it kind of uses an average of the port area as a guide. John Robinson went on to it a little bit further in his book, and there was some data towards the back that showed you how to write a program to work it out. Quite basic, but I believe it's probably similar to the stuff that's in Gordon Blair's book, Professor Gordon Blair, from the Queen's University Belfast. And that's some of the graphs that I'm going to show you now and talk through it, where they derive the data from. I believe they did a lot of R&D and a lot of engine testing in-house at Queen's University Belfast over the years, and they built up a lot of empirical data. So you'll see it's the best fit line that they actually use for the data, because the results are all over the place, because it depends on the tune of the engine, the development of maybe the scavenging flow, the exhaust flow, the packaging, what the application is. Is it a lawnmower engine or generator engine or Grand Prix engine? So yeah, so we'll take a look at that, at where that comes from and how it's used to then establish the areas we required, or the time areas we require for X amount of power out of our engines, and how that then links onto the time flow area that I do with the TorqSoft software. Right, this is part of Gordon Blair's two-stroke design simulation of two-stroke engine book, and there's some stuff highlighted a bit. So I talked about the empirical data, and he does say there exists a danger that empirical guidance to be given will be guarded as the final design, the quick fix formula so beloved by the human race, and desirous of cutting corners and solutions to the problem. So that's it. So that's this master system, this stored data gives you a starting place really for the simulator, for an application, and then his goal was to use that as a starting place and then use the simulator to find out actually what the geometry of the engine, etc., does require. And I know Niels van Niekerk is of the same opinion, particularly the STA's there as a guidance, but you've got to then run the sims to find out actually what is the optimum, and then actually go and test it for real. So yeah, specific time area. It's the potential for that porting to produce a specific performance characteristics to the engine. So X amount STA will give you X amount of power, and that's generally, he's proven, I haven't read it, but performance characteristics for an engine are related to the mass flow rates of gas travelling through the ports of the engine. So basically, M dot, the mass of combustible mixture that goes into the engine and back out, it directly relates to the amount of power. And here you got I call it angle area. So this is basically a plot of port opening and the area of the port at different. So here the exhaust port's open. Just as it opens, you've got a small area, and then as it's fully open, you've got a large area, so 400 millimeters squared. And then as it closes again, you can see it's symmetrical. I'll just try and draw that out. So it's really difficult doing it with a camera in the way. Try not to go. So if you've got say an exhaust port square like that, and then you've got the piston next to it. So as the piston opens it, you've got X amount of area. So that's area, and that is degrees. Crankshaft, say the port opens here. At the top there's nothing, then it opens to this degree and it's got that much area, and then it opens again, So now we've got that and that open at this degree, so it might be double. And then again, further degrees again, and then fully open, you're going to have that whole area open, and then as it closes, it's going to go back opposite until the port is closed. And the area under there, that's your angle area of basically how much area you have per degree of crank rotation. If you then work out the time for that area, because obviously degrees, engine RPM, so at different RPMs, fast the engine's going, the faster this port is going to be open, and that's where you get time area. When you bring in that time, so from the bottom, instead of having degrees, you'd have time, and that would be the time the port was open instantaneously. From that, we talk about specific. So what is specific? Time area. It's basically the time area you get divided into the cubic capacity of the engine. So it's transferable. It doesn't matter whether it's 50cc or 500cc. The amount of time area you need for that power is basically universal. So it disregards the cubic capacity of the engine. So really, that's the specific time area as I understand it. Anyone think any different? Then let me know in the comments. So as you can see there, that is the amount of time area you've got. And basically, if I need, this is my X amount of combustible mixture that I need to get through, say, that exhaust port. Can I flow that much through there in the amount of time I have with the time area available? And if the answer is yes, well, I should make roughly the power I require. If I can't, then because the mass m dot of gas is directly related to the power, then if I can't get enough gas through in the time area I've got available, I won't make the power. So then I'll look at it, go, I haven't, and then we'll probably look at maybe raising the exhaust port, and then raising the exhaust port will then obviously raise this, and it will gain you more specific time area, in which case, I can flow enough mass of gas now, so I will get more power. Moving on, obviously the angle area, there's a lot of maths, or math if you're American, to work out the STA, to know the units of second per metre. And this is some of the data that Queen's University had. So for inlet ports, for example, if you want, at whatever your desired RPM, you want, I don't know, 10 brake mean effective pressure, 10 bar brake mean effective pressure, you will need this amount of specific time area, and 50 times 10,000 is the specific time area you need. Again, transfers, they've got a top and a bottom, but as you can see, there's a scatter. So some engines had made more brake mean effective pressure with less specific time area, which says that maybe the rest of the design of the engine was very complementary and it was very well matched, or had really good transfer ducts, really good scavenging flow. So that's that. Because there's another one roughly the same here, and it's making only 8 bar, so it might have really rubbish transfer ducts. And I think this is a minimum and that's a maximum. So I guess for high performance, you're looking at that maximum. And there's some more there for the exhaust ports, and as you can see, you've got the same. So for what, 11 bar there, it's saying you need what, 155, whereas down here it's only getting 6 for the same amount of specific time area. So it might be a bad exhaust duct. It may be it doesn't have a tuned exhaust system on there. So there are anomalies, and these are just best fit lines which get you in the ballpark for your design ahead. However, from what I've heard, a lot of people who use this, I think TorqSoft software use this data as well. Correct me if I'm wrong in the comments, but as a start for 10, it's really good to get you in the ballpark. So leads us on to the time flow area program, this time for transfers. As we said before, empirical guidance is good for a starter you can develop it within a sim, within real world testing to find out, because it is an average, and again some of the engines don't flow as well. So to take it a step further, you've got the transfer time flow area program from TorqSoft, and as it says here, time area calculated by the traditional method, i.e. this one, using the actual transfer port dimensions, is a fantastic tool. However, there are some cylinders that just don't flow as well as the calculated time area suggests, as illustrated here. Which would result in poor performance and a lot of wasted development. Using the TorqSoft time flow area program, you give more reliable power predictions. So is what this is doing. It's then, I've used time area to get me into the ballpark. This is actually seeing, will my transfer ducts or my exhaust duct flow actually sustain that amount of mass flow for the power I require. Scavenging flow. So the direction of the scavenging flow, I said that can affect us as well. So we might have enough time area, we might have the flow time area as well, but if it's pointing in the wrong direction, it won't efficiently scavenge the cylinder, i.e. remove all the combustion gases that are lurking around the cylinder. So what we want is a good directional flow of scavenging gases going towards the back of the cylinder, going up over the combustion chamber and coming back down and purging them out of the exhaust duct. Frits Overmars has done a really good article on his Leaning Tower of Pisa concept, and gives some mathematics to use to work out the net overall column direction, and it gives you some pointers of where roughly you want the net angles of the transfer ducts to point to give you a good scavenging flow. I'll leave a link to that in the description. So what am I going to do today? So I said some two-dimensional in Mota 7. Mota 7, it's only 2D, so if you cut that cylinder down the middle and looked at the plane that sits there, flat like that, and what it shows is the gases, direction of the gases going that way, up and down and left and right, and how that affects the scavenging of the cylinder. So we'll look into that. Mota doesn't make any bold claims about this is how you design a scavenging system. It's purely there, well, I say purely, it's more there for education and the effects of the direction. Obviously, if it's directional flows going out the exhaust, we'll look at that, and we'll also look at a more traditional pointed back towards the rear cylinder and look at how the purity is affected within the cylinder itself and how it ultimately affects power. The instructions from Mota, and you see here, so thick black arrows indicate the specific direction of flow or fluid entering or leaving the ports. So the exhaust duct, I think that was about 10 degrees down, and you can see here, so that's the angle, that 90 degrees, that's 0 degrees. So if I'm saying 100 degrees, it's slightly back, 135, it's even further back, and then when I do one at 80, it's actually going that way. On mine, it just lumps it into one big, all the transfers flowing through this one big transfer duct, although there are 3 separate ducts, and these are the angles. So obviously the exhaust flows outwards, and then, so for the standard one, as it came, the flow is coming into the cylinder at about 135 degrees. So on test 3, I've canted it just back a little bit, so say 100 degrees, so that's 90, and then on test 4, just exaggerate a bit, that's 80. So it is naturally going towards the exhaust. This one isn't going to the exhaust itself, however, it's not as far back as the standard, which is 135, and that's what we're going to look at now. So here we have the two-dimensional flow prediction by Mota 7. So I'm just going to pause it quickly. So you can see the yellow box to the right, that is the exhaust port, and the yellow box at the bottom is the transfer ducts, and in this model it's actually lumped all the transfer ducts into the same square that's where they eject into the cylinder. We can look at purity, pressure and temperature, and that's indicated by the colour. As you can see, the green's now coming out. That's indicating 100% pure fresh gas that's coming in, and the red is indicating that's the burnt gases, as you'd expect. So now you're seeing the pure gas coming in up the back wall towards the top of the combustion chamber, and it will eventually come around and it will push out that spent mixture out of the exhaust duct. And also notice there are arrows as well, and if I zoom in you can see these arrows, they give the direction of flow. So as it keeps going, you can see the piston coming up, there's a bit of a circle going round. You can see some of the gases coming back in from the exhaust duct, so pure gas is coming back in, and then it just stops towards the end and starts to go back out again, and then that's what we're left with in the cylinder, and then the process starts again and again and again. Okay, results of that sim, you can see about 30 horsepower for this cylinder, and that is with the transfer ducts aiming in at 135 degrees, so that is towards the rear of the cylinder. So then I ran another couple of sims. I did one at 100 degrees, so that's slightly to the rear, and another at 80 degrees, and that's slightly towards the front. For comparison, now I bring you the 80 degrees entry to the left, so that's going slightly forward out the exhaust duct, the flow of the transfers, and then on the right we've got the 135 degree standard. Bear in mind with me, as you can see, the pistons, they do move very slightly different. I'm playing around with the speed all the time just to try and get a match, but if you watch this now we should see the difference in so the angle back, directional flow from the transfers, it's going up the back of the cylinder, and as we've seen before, it's scavenging. But where the flow is just heading out towards the exhaust duct, we can see that it's not actually going up the back of the wall, it's not clearing out those burnt gases at the top, and it's basically just going out of the exhaust duct, which is obviously not helping us. So you've not got a lot of fresh charge in the cylinder when it does finally close the exhaust port. But another of the issues is you're pouring a lot of cool mixture into the exhaust system, which is cooling it down, and effectively the exhaust duct, the exhaust system goes out of tune, and as you can see all the way through, fresh gas straight out the exhaust, not actually scavenging, whereas angled back scavenges quite nicely. So yeah, so the results, blue line, that was the standard, so that's 135 degrees back. The pink, I actually canted it to 100 degrees, so still slightly to the rear, but even then you can see it has had a detriment on the power, particularly on the over rev, because there's more cooler gases going in. And then the bottom graph, it's hardly making any power, totally out of tune. All the cool gas and exhaust, it's out of resonance. Plus there's very impure mixture within the cylinder as well. Lots of spent gases there that aren't going to combust properly, leading to less power. So a bit more data to back it up. On the left is the standard cylinder. So peak temperature is around 2000 degrees Fahrenheit, whereas if you look on the right, that is for the 80 degree outlet angle, and that is 600 degrees. So yeah, a lot cooler in the exhaust. And again, looking at the purity, so on the left, see purity, it's pretty much nearly 1 in the cylinder, and that's for the standard cylinder, 135 degrees, whereas with the 80 degree entry transfers pointing towards the exhaust, it's around 6.8, and it drops down even lower than that, down to about 0.5 at some point. So massively bad. So finally I'm going to hit calculate, and there you can see, so 22.4 horsepower from the transfers, and then if we compare that to the STA calculating engine mod just off the port area itself, you can see there 26.2, so we've got about 4 horsepower difference. hopefully I've managed to get across some of the differences, some of the issues with the specific time area, time flow area and scavenging flow direction, and how that all plays a big part into how much power we can get out of a two-stroke engine. I'm keen to do some more testing with the flow testing, see if I can improve the flow. I'm also keen to look at different directions and that, see if I can improve that. I don't know how easy that can be. If anyone's got any ideas, let me know in the comments. And as you know, previous videos as well, which should come up here, about exhaust flow testing that I did in a previous video, and also one up here where I look at changing the timing of the exhaust, increasing the specific time area to hopefully to get some more power. Thanks again for watching. Please like, subscribe, share, it really does help. Thank you.